Díomh a gcuin ús agus cóide. Is mise an talamh pádraig ó gaire uachtar an cadamh. Is mór an ordom fáilte curramh go léir go dtí acadamh ríga na hÉireann inniu. Good evening, everybody. I'm delighted to welcome you all to the Royal Irish Academy for tonight's discourse entitled The Geometry of Chaos, From Climate Change to Foundations of Quantum Physics. So as introduced, my name is Pat Gyrey. I'm the President of the Royal Irish Academy, and also present this evening are the Academy Treasurer, Professor Mary Kelly, and we send our best regards to the Academy Secretary, Professor Mary O'Dowd, who unfortunately is ill this evening and cannot join us as a result. So Academy Discourses are the oldest and most renowned series of talks in Ireland. The first discourses were presented in 1786. Historically, they were the occasion reserved for the most distinguished academics, they still are, by the way, to reveal and discuss their work in public. We now record these discourses, I don't think they did in 1786, and they are available on the Academy's website for you to peruse and watch at your leisure. Before we begin, we have some short Academy business to undertake. The minutes of our last discourse, entitled Grange Gorman, From the Era of Neglect to the Era of the Asylum and Back, which was held on the 13th of December 2023, were posted online. Since our members did not inform us of any issues with these minutes, I will take these as approved, and I will sign the minute book after this discourse concludes. So it's a great pleasure to welcome our esteemed speakers for this evening's discourse. Professor Tim Palmer is a Royal Society Research Fellow at the University of Oxford. His PhD was in general relativity theory, but he spent much of his career researching the nonlinear dynamics of our climate system. Amongst other things, he discovered the world's largest breaking waves in the stratosphere and pioneers the development of probabilistic ensemble prediction techniques for weather and climate forecasting. He was awarded the Royal that's easy for me to say, the Royal Astronomical, which is a very big word, it's an astronomical word, Society's 2023 Gold Medal for Geophysics for his outstanding work in advancing the understanding and prediction of climate and weather. Of course, Tim, in Ireland, if it's not raining, it will be soon. So there's the prediction for our weather. Professor Palmer was elected as an honorary member of the Royal Irish Academy last year. His recent book, The Primacy of Doubt, From Climate Change to Quantum Physics, How the Science of Uncertainty Can Help Predict and Understand Our Chaotic World, will be available to purchase after this discourse. And I'm sure if you ask nicely, Tim will also sign a copy. For the response, it's Professor Luke Drury MRIA. He's chair of the ALLEA, the All-European Academy's Open Science Task Force. He was a former president of the Royal Irish Academy from 2011 to 2014. So without any further ado, now to the discourse. Professor Palmer, over to you. I look forward to this.
Thank you very much. It's a great honor to be here. You know, I was actually feeling quite comfortable about this talk until about 5 minutes ago when I asked the president how many discourses there are a year. I'd assumed they were kind of every other week and they just grab people off the street to give talks. But no, there are 4 a year and they're very serious talks. So now actually, if you feel a bit of nerves, this is as a result of my mistake. I should never have asked the question beforehand. Now, I haven't actually had a go at these slides, but they do seem to work. So that's the title of my talk. I'll try to explain a little bit about what that strange object is in the background. And as a kind of just unashamed advertisement, I am going to talk about different topics, let's say, in this book. Now, you know, as Pat said, it's sort of a book about the science of uncertainty in different areas. But there is really a sub-theme going through the book, and I want to tell you what the sub-theme is. If you were to ask a group of physicists to name the greatest theories of 20th century physics, without any doubt whatsoever, they would say quantum theory and relativity theory. So Einstein's theory of gravity, general relativity, the culmination of his theory of relativity, and the then subsequent quantum mechanics, whose, you could say broadly, proposed by Schrödinger, who was, of course, lived here for many years in Dublin, and Heisenberg. What I'm going to try to persuade you is that we should actually think of three sort of triumvirate of theories, and chaos theory also vying with these two for a kind of position as a preeminent theory of 20th century physics. Now, to be a great theory, I think, it has to tick two boxes. One is that it has to make very fundamental, improve our fundamental understanding of nature. But it also must be a practical theory, must have practical consequences in the real world. And I shall try to focus on both aspects of that and give you my own perspective, at least, on some of these things. So what is chaos theory? Well, chaos theory, I think a common perception, which is not a bad perception, is that it's a theory about relatively simple systems that can have very complicated behaviors. And this is a picture in my office in Oxford of myself and a couple of my group looking at a pendulum, which instead of just having one pivot, if you like, at the top, it's got these two pivots, so there are two arms. And it's a kind of time-lapse photo. There's a little LED at the tip of the pendulum, and you can see just from the time lapse that the motion of that tip is really very complicated. It would be very difficult, for example, to describe that LED path with a simple equation. Very complicated system. So that's one aspect of chaos theory. Another one, which is very strongly related to that, is this notion that chaotic systems are very difficult to predict, because any slight uncertainty that you might have in the starting condition for your prediction can end up making the prediction incorrect, let's say. And I can illustrate that with a very nice animation that was made by a colleague of this same double pendulum. So there it goes. And you might think we're looking at one. Well, no, you can see we're not looking at one. We're looking at a whole ensemble of animations of this double pendulum. And you can see how, although they had started almost from identical starting conditions, they end up looking extremely complicated. So there it goes again. So chaotic systems are systems where uncertainty grows technically exponentially with time. This is another practical, let's see, here we go, practical example of a chaotic system. It's a pendulum that's affected by magnets. So it's a sort of metal pendulum which goes under these magnets. I sometimes like to call this the executive decision maker, because you buy 1 million shares of the company that it ends up on. You see, you might think, oh no, it's going to stop there. But see, so it's very difficult, does actually end up stopping there. So, and we'll come back to this example later on in the talk. So that's another illustration. Now, the object I showed right at the very beginning in that title slide was discovered by a guy called Ed Lorenz. And he was an American meteorologist, somebody actually I knew quite well, based at MIT. And back in the 1960s, he was kind of plagued by statisticians from MIT who came up to him and said, predicting the weather is very simple. You just need to find a day like today back in your archives of weather, and you use, whatever happened a month after that analog day. That's your prediction for today. So the statisticians were trying to tell him that weather prediction was very simple if you viewed it as a statistical problem in statistics. And Lorenz felt that this idea was misguided, and he wanted to come up with a simple model which kind of disproved this idea. So the statistician's idea was basically that the weather would repeat itself. It would be periodic. Every now and again, it would just go back to where it was maybe 50 years ago, and everything would repeat. And he felt that this idea was incorrect. And it would take an hour to tell you about these equations, and in fact, I'm sure a lot of you, are not mathematicians, so you don't really need to know. But he came up with these three equations, which make use of, the reason I've got Isaac Newton there as well, is they make use of Newton's calculus to describe them. So he kind of boiled the weather equations down to a very idealized set of equations, which turn out to have this property of chaos. Something at the time I think most of his contemporaries would not have believed was possible, that you could boil down complicated equations to just three and exhibit all the complexity and difficulty of predicting weather. So I don't want to say too much about these equations, but the main thing to bear in mind is there are three variables. So these capital letters X, Y, and Z represent variables. A variable, the number varies. The other things like the Greek letter sigma and the little r and the little b are just parameters which have fixed values. And the left-hand sides of the equations, that little dot above the X, the Y, and the Z, that's where the Newton calculus comes in, because this is what's called the time rate of change. So how rapidly X, Y, and Z are changing with time depends on the values on the right-hand side. And with those equations, you can basically put those into a computer, which is what Lorenz did, some of the early computers he had access to. And starting with a set of initial conditions, you can see how the system evolves. And this is actually an example of that. So it's kind of fortunate, because the equations only have three variables, that you can represent the space of variables in a three-dimensional space. It's kind of a coincidence, but X, Y, and Z, these are not physical. It's not like the physical dimensions of this room. These represent fluid motions. It's a sort of the connection to the weather is a little bit complicated, and we don't need to go down that route. But basically, these are three variables that can be represented by three axes in a three-dimensional space. And what you see here is basically a computer doing this, what's called integration of the equations from an initial state, which is one of with the endpoint on the left of the equations, and we just run it for a while, and it sort of goes round in a circle and doesn't quite go round forever, and it goes round a different circle. So Lorenz discovered that. He thought that was interesting, and then said, well, what would happen if I carried on and on and on and on and on, as long as the computer would allow me to carry on? And he found a really intriguing structure to this sort of solution of the equations. And although Lorenz, if you read popular books, you often see Lorenz and Lorenz's model being used to illustrate the butterfly effect and chaos and all that sort of stuff, I think the real genius, and the thing that perhaps he's not given enough credit for, is this discovery of what this structure is. Because what he realized, and I perhaps won't read, you can read it if you like, that's from his famous paper in 1963. Basically, he realized what this thing was what we now call a fractal. In other words, the trajectories, this wasn't just a simple sort of one-dimensional curve that just looks very complicated. Neither was it a sheet like a piece of complicated origami, nor was it a three-dimensional volume, but it was something which we now call a fractal, which is characterized by a dimension which is not a whole number. So it's 2 point something, something, something. And the simplest type of fractal is the thing I've shown on the right, which is called a Cantor set, which was discovered by the German mathematician back in the 19th century, Georg Cantor, which is basically taking, let's say a line and cutting out the middle third of that line, throwing that middle third away, then cutting out the middle third of the remaining bits, and keeping cutting bits out, and on and on and on. Now, this fractal, the point about this fractal is that it has a structure which never disappears as you zoom into it. So the more you zoom in, you still see that structure. In fact, the structure keeps repeating itself. Now, I haven't got any slides of this, but those of you who've heard of a thing called the Mandelbrot set is a very famous example of a fractal which, you zoom into it and you keep seeing this incredible structure which just keeps going on, no matter how deeply you delve into it. And the same would be true of that, what is now called a Lorenz attractor. It's the geometry, if you like, that's produced by these equations. And the reason why I think this is remarkable, and in a way this is where the connection to Newton suddenly goes away, because for Newton, the notion of geometry would mean the kind of postulates of geometry that Euclid, the ancient Greek mathematician, derived, which describe things like spheres or ellipsoids or something like that, which of course Newton had made great use of in his theory of planetary motion. But a sphere or an ellipsoid looks boring if you zoom into it enough. It just looks flat. You lose the structure of the geometry as you zoom in. Whereas a fractal, you never lose that structure. It's always there. So there is something remarkable. In fact, I'm going to move on to the next slide. There's something remarkable about this geometry. And the way I'm going to illustrate this is that it actually bridges the divide between the mathematics of Newton, the really kind of classic 17th century mathematics of calculus, which produce those differential equations. But the equations produce this geometry, and as I'm going to show you in the next few slides, it links to some of the very, very, very deepest theorems of mathematics of the 20th century. So those are three great 20th century mathematicians, the Austrian, I think, Kurt Gödel, Alan Turing, who I discovered his mother was from Ireland, and the parents got married somewhere very close to here in the church in Dublin. And the one on the right is Andrew Wiles, who's a professor of maths at Oxford, but possibly the most famous mathematician alive today, because he famously proved something called Fermat's last theorem, which I'll come on to very briefly. So what I'm claiming then is that whilst Newton would have looked at those equations and said, oh yeah, I understand those. Those are nonlinear differential equations. He might have even used those exact words. He would have been completely shocked and bamboozled, if you like, by the geometry that those equations produce. And as I'll say in a minute, that geometry links very closely to some of these very profound, really profound mathematical results of the 20th century mathematics. So Gödel is known for his so-called incompleteness theorem. It's a kind of result, very profound result in mathematical logic, which basically says that the set of mathematical truths is much, much greater than the set of mathematical theorems that have proofs. So it's a kind of, as I say, it's kind of almost very metaphysical result, but quite deep. And a very specific example of that was proven by Turing. And actually, to come up with the proof of this specific result, Turing basically invented the modern computer, the structure of a modern digital computer. But this was back in the 30s, before there were any digital computers. So what he took on was what's called Hilbert's decision problem, which basically says, can we design an algorithm, which you could today read as a computer program, if you like, which you would feed in some theorem, potential theorem, and basically what you want is that the program looks at it and churns around a bit and comes up, this is true or this is false. So is there such a procedure in principle that could determine the truths or falsehoods of this famous Hilbert decision problem? Hilbert was one of the kind of great mathematicians of the early 20th century. And in a way, consistent with Gödel's theorem, what Turing showed was that, no, this was not possible, that essentially limiting the use of computers for proving mathematical results. I do discuss a little bit in my book, because it's something that Roger Penrose, who's very much a mentor of mine in my PhD days, has a lot of discussion in his books about the relevance of Gödel's theorem and indeed Turing's results to the notion of whether artificial intelligence can really understand mathematics or indeed understand anything. And Penrose argues that because of this limitation and because AI is inherently algorithmic, it cannot understand in the way that we understand things. I go into that a little bit in the book, but I'm going to sort of jump over that a little bit right now. I mentioned Fermat's last theorem. It's called Fermat's last theorem, but Fermat never actually proved it. He famously wrote in one of his books, in the margin, I've got this wonderful proof, but there's no space in the margin. It reminded me somebody on the New York subway had written under a sort of an advertisement, I've just found a wonderful proof of Fermat's last theorem, but my train is coming and I've got no time to write it down now. It's a similar theme. But he proved it, Andrew Wiles, in the 1990s. Really very kind of super famous result, because this is a problem that have been taxing all the greatest mathematicians over the centuries since the time of 17th century Fermat. And so I just wanted to briefly tell you the link to chaotic systems, and in particular this notion of geometry of chaos. Because there was a nice paper by mathematician Simon Dubé back in the 90s, who actually showed that you can actually, all these undecidable problems, the problems that can't be proven by algorithm, can be reframed in terms of problems in the geometry of fractals. So a very simple example could be, is there an algorithm for deciding whether a point lies actually on Lorenz's attractor? Because there are always gaps, and the more you zoom in, there are gaps within the gaps and so on. And basically, the answer is you can't decide by algorithm whether a point lies on the attractor. And basically what Dubé did was take all the classical undecidable problems, like Hilbert's decision problem, proving, getting an algorithm for proving whether a theorem is true or false, and showing it has an analogous formulation in terms of the geometry of fractals. And then in terms of Fermat's last theorem, so Andrew Wiles is what's called a number theorist. Number theory, it sounds like number, well, that's really elementary, numbers. But number theory is probably the most complicated of all branches of mathematics. And it's so complicated, they don't even use the kind of numbers that we would recognize as numbers. And there's a whole area of mathematics using a type of number which even physicists, I think, probably don't really understand, called p-adic numbers. But it turns out that the simplest way of understanding p-adic numbers, what are called p-adic numbers, is that it's a type of number system that you need if you want to do arithmetic and algebra and calculus and all these sort of things on fractal geometry. So I think probably I won't dwell upon that, so I'll be taking too long. But there's a very, very strong linkage between these numbers that Wiles and his colleagues used was absolutely central to his proof of Fermat's last theorem and fractal geometry. So that's why I'm saying there's this really curious link between Newton and Lorenz on the one hand, and then down to these great mathematicians of the 20th century. Later in the talk, I'm going to try and make a claim there's also links to some of the great physicists of the 20th century, but we'll come on to that a little bit later. So this is a little bit esoteric, right? So I'm going to try and jump to rather more practical issues and things that I have been, have taken much of my career working on. So you might get the impression that a chaotic system is inherently unpredictable. And to some extent that's true in the sense that if you wait like forever, ultimately the system becomes so sensitive to the tiniest of errors in the starting conditions, it's impossible to make a prediction. But if you just focus on, what are relatively short-term predictions, a thing that characterizes a chaotic system is that some initial conditions can be very predictable and some initial conditions can be very unpredictable. So this is an example of that for the Lorenz system. So what we're doing, say, take the top left. If you imagine that little ring at the beginning, at the very, very top left of the top left, you could think of that as a little ring of uncertainty. So the true initial condition, you don't quite know where it is, but it's somewhere inside that ring. And then we're going to march forward in time, maybe, let's say if it was talking about weather, it could be a day or 12 hours or something. And what actually happens is that they make a jump from the left-hand wing to the right-hand wing. In terms of weather, you could think of these as different types of weather, stormy weather to settled weather or something like that. And you can see actually that ring, if anything, it actually shrinks a little bit. So the uncertainty at the final time is very, very small. So in this situation, you can be extremely confident about that the truth is somewhere in that little ring, sort of slightly distorted ring, at the end of that sequence of rings. On the other hand, if you just move to the top right now, if you move that initial ring like down a little bit, and then again evolve it in time, it kind of distorts into a bit of a sort of banana shape. And in fact, it's a very stretched out banana by the end. And you're not really sure at all whether the true state has actually made that jump from, let's say, stormy weather to calm weather, or it stayed on the stormy side. In fact, all you could really do is say, well, there's probably a probability of, 60% or something that it stayed stormy, and a 40% that it's made a jump. And then the bottom one, the uncertainty absolutely explodes. So this really illustrates this concept of what I call intermittent instability, that it's not like chaotic systems are always unstable and always unpredictable. The instability that causes the unpredictability can be localized in a rather small part of this attractor. Now, many years ago now, I joined a place called the European Centre for Medium-Range Weather Forecasts in Reading, which Ireland is a member state country. And in those days, the forecasts were definitely very, what we call deterministic. It will be sunny tomorrow, it will be rainy the day after that, and so on. Very, and the forecasters on the TV were instructed to be very sure of themselves, And I was aware of this stuff, and I was saying, but look, this is a dangerous strategy because we're going to be caught out. Now, the alternative you see would be instead of running a single forecast, you'd run a whole load of them, 50 forecasts, from very slightly different starting conditions, and look to see, are they, after a week or so, is it like the top one where they all stick together? Or is it like the bottom one where they all explode apart? Because if it's like the bottom one, then you're not going to be able to say anything very definite about the weather, in a few days' time. And I had lots of very kind of esoteric discussions with my colleagues about this. But fortunately, nature decided, because in 1987, in southern England, there was the mother of all storms, October 87. And famously, the BBC weather forecaster that the evening before came on and said, oh, it'll be a little bit breezy, but nothing to worry about. And, famously, the Kent town of Sevenoaks became No Oaks. And there was complete devastation. And the director of the Met Office was under extreme pressure to resign because they were giving all these millions of pounds for big computers and satellites and things, and you can't even predict the worst storm that's ever happened a few hours before. So this was a very good example of that bottom situation, and as I say, it kind of people realized they had to rethink the way weather forecasting is done. So nowadays, what's called ensemble forecasting is pretty much routine around the world. And one area where it's had a very, you may be annoyed actually, because when you look at your weather app and you want to know whether it's raining, it just gives you a probability, and you're going, oh God, why can't it just tell us when it's going to rain? Well, I'm afraid that's a consequence of these ensembles. This is what they're looking at, the number of ensemble members where it's raining in Dublin tomorrow or something. And if only 80% of the ensemble members it's raining, then that's the probability it's going to rain, and that's the best we can do. Now, you might find that's a bit of a nuisance, but let me just show you an example of an area where it's having a really important, I think, humanitarian impact. So what I'm showing on the left are three examples, and they're supposed to mirror the three examples of the Lorenz attractor. So I showed the very predictable, the not so predictable, and extremely unpredictable parts of the Lorenz attractor. Well, here are three ensembles of tracks of hurricanes or tropical cyclones, depending on the part of the world you are. And the top one, and we're looking sort of typically about a week before these things make landfall. And the top one is a cyclone called Cider, and you can see at that range, although there's a bit of uncertainty, if you were head of the Bangladesh Met Service, you would know there's a pretty good chance something pretty terrible is going to happen in a week or so, and you would send out warnings for people, particularly Bangladesh, where a lot of people live in very low-lying areas, on the Brahmaputra or Ganges, wherever, and prone to storm surges that these hurricanes would produce, tropical cyclones. So very high probability. So you could pretty much send out the warning straight away, take action, move your livestock, whatever, to higher ground, and yourselves indeed. The middle one is the famous Hurricane Katrina that hit New Orleans, again a week before. And you can see there is actually considerable uncertainty about whether it's going to go into the Gulf of Mexico or go up the Florida coast, the Florida, what do you call it, panhandle. So at that range, actually, it would be very difficult to be absolutely categorical that somewhere like New Orleans should evacuate. The governor would be at least alert to the fact there was a risk of something happening, but you'd have to wait another couple of days before you could probably take action. And then the bottom one was called Nadine, which is of no great significance except for the fact that even whether it was going to go in towards Europe or back towards the Caribbean was uncertain. It was completely unpredictable. So what's the relevance of this? And it's to do with the way now humanitarian agencies are responding to these extreme events. Because in the past, particularly in the days of just deterministic forecasts, they were too unreliable to be able to take precautionary or preemptive action. So typically they would only go in with shelter and food and medicine and water and so on until after the event had hit. Because if they went in on the basis of every forecast of a severe event, they would run out of money almost immediately. But now what they can do is make a very informed kind of cost-benefit type analysis decision. So they work out ahead of time how high a probability for an extreme weather event to occur should be for it to be worth taking action. So obviously if it was 100%, it would be worth it. If it was 90%, it would be worth it. If it was only 10%, then 9 times out of 10 they'd be putting in emergency provisions which weren't needed. So you can do a kind of a cost-benefit analysis based on how much money you've got, how much resources you have, and so on, to determine a threshold probability above which you take precautionary action. You don't wait for the event to happen. And that's now being called anticipatory action. It's a very big program in the UN, the Red Cross, Red Crescent, all these humanitarian organizations going in advance. And it's being made possible because of quantitative risk estimates of these extreme events, which has been made possible by Ensemble prediction. Now, so I talked about the weather quite a lot. I just wanted to say to start with, I wanted to say that the first person to realize that there were chaotic systems was actually not Ed Lorenz, but the French mathematician, physicist Henri Poincaré. And if I can get this to work, well, what I'm going to show you and he was looking at the solar system. Now, you might think the solar system is the absolute archetypal model of predictability. The Earth goes around the sun once a year, right? What could be more predictable than that? We can predict eclipses, decades ahead of time. But he actually showed that you shouldn't take this for granted. So I'm going to show you an illustration of 4 bodies which are kind of gravitationally bound. It's a slightly contrived example, but it illustrates the principle. So you've got these 4 massive bodies, and they're going to orbit around each other on what look like very nice periodic sort of ellipses. And it looks like it's extremely boring. They're just going around. Everything's super predictable until... So don't take it for granted that the Earth is going to go nicely around the sun once a year. Actually, there is a serious possibility that something like this might happen to the planet Mercury in maybe a few million years. But this is, again, a rather nice example, again, of this kind of intermittent instability. It's not manifest all the time, it's just hits. And in the book, I've tried to discuss a number of kind of topical areas like, well, COVID, economic prediction, conflict prediction. Our health is, as a community, is pretty sort of reasonable most of the time, but then suddenly out of nowhere these pandemics come. The economy ticks along quite well most of the time until suddenly we get some big financial meltdown. And we sort of get along with each other until we get these wars. So are all these examples of nonlinear intermittent instability? And in particular, can we use the methods of ensemble prediction to give us heads-ups, if you like, heads-up, whatever the phrase is, of impending instability and meltdown? So I have chapters on this. I had an email from Ben Bernanke, who said that he's got my book to read as part of the review of the Bank of England's lousy GDP and inflation predictions. And I have a chapter, as I say, on economic prediction where I'm a bit critical, let's say, of the way the economists deal with the economy. But anyway, that will be going off at a tangent, which I won't do. In fact, I want to come back to that example at the beginning of the executive decision maker, because sometimes people say about climate change that they know that the weather is chaotic. They know deterministic weather forecasts can go wrong after a few days. So they say, well, how on earth can you possibly predict climate change 100 years from now if you can't predict the weather 5 days from now? And my typical response to that is to say, well, it's not the same type of problem. And I can illustrate that by, well, I will illustrate with this animation. So we return to our executive decision maker, but now we should think of these 4 magnets as different types of weather. Maybe cold weather on the left, warm weather on the right, rainy weather, the one near to us, dry weather or something, the one further away. So the magnet, the animation I showed you earlier, you take my word for it, but I mean it's fairly obvious, isn't it? That as long as the thing is sitting kind of like flat on the table or whatever, on average the pendulum is going to spend a quarter of the time going around each of the 4 magnets. So there's no bias there's no preference for the pendulum bob to be over one magnet rather than the other. But what we're going to do now is bias the system. We're going to slide a little wedge. Here it goes, and off it goes again. And again, it's chaotic. You can't say for certain where the pendulum will be, but you can kind of see, I think, by eye that it's favoring the yellow one on the right. The probability is increased. So if that was the warm weather, that we'd be seeing an increased probability of warm weather. So that's the idea, and in fact it ends up there. So the idea is the wedge is representing our emissions of carbon dioxide into the atmosphere, and that is kind of biasing the statistics of weather in a certain way. And that, if you view it in that sense, it's a predictable. It's a well-posed, predictable problem in the sense that, you can't say what the weather's going to be like on the 1st of June 2021, 22 or something. But what you can say is the likelihood of certain types of weather in 21, 22 compared, say, to what we see today. Now, I did want to flag something I only learnt recently. A colleague of mine, a fellow at the Academy, Ray Bates. And I think Ray I value this in our community, people that are skeptical and ask questions about climate change. And he did have some deep questions about climate change. And what I would say is I don't think he didn't question the model I just showed. There is still a big uncertainty in a sense, which is how big that wedge is, how thick the wedge is. And that's a very, very, very difficult problem because I said to you it's about CO2, and it is about our emissions of CO2. But the size of that wedge, how much that wedge is changing the statistics of weather, is not purely about the CO2. It's about the knock-on effects that CO2 have on the water cycle, things like clouds and water vapor. These are things which can amplify, or indeed in the case of clouds, they could damp the climate change signal. And, the size of that wedge, how much it's perturbing the weather systems, critically does depend on these estimates of what are called cloud feedbacks and water vapor feedback, and indeed other types of feedbacks, which are very complex problems. And I go at great length in my book to discuss these uncertainties. And, I say to people, if you hear somebody say, we're all going to die from climate change, you can discount that as much as somebody will say, oh, climate change is insignificant and we don't have to worry about it. Both of those views are unscientific. The fact of the matter is, if you want to represent climate change, you have to represent it in terms of probability distributions of things. In a way, a bit like the weather forecast is probabilistic, climate change is probabilistic. And what we decide to do about climate change, in other words, whether we take action now to lessen the risk of these extreme weather events, is a matter of balancing the consequences of climate change with the costs of action. And that's not a purely scientific problem. It's a political problem. It's an economic problem. So my own view is it's kind of important in this whole area. And when the two get muddied, it leads to more heat than light, if you like. That we have to separate out the science from the politics, and they are separable. But you have to understand, if you making that decision about what we do about climate change is not something that science can answer by itself, because you have to make value judgments. So people that just say, listen to the scientists, that's actually not strictly correct, I don't think. Pat, how am I doing? I'll carry on for another few minutes. I've got a couple more things I wanted to say. I'm going to skip over this a little bit quickly, but I just want to bring this up because it involves a very famous Irish mathematician, physicist, George Stokes, who basically, with Frenchman Claude Navier, basically wrote down a very famous equation in physics and mathematics, which is the equation for a fluid, like the atmosphere or the ocean. It's a formulation of Newton's second law of motion for something very complicated like a turbulent fluid. And this is central to climate models. So in coming up with predictions of climate change, Lorenz's model is no good at all. We have to use the full, what are called Navier-Stokes equations. But these are devilishly difficult to solve. You need a big computer. And what you do with a computer is you try to represent the climate system with little boxes called grid boxes. And there's an assumption that within each grid box, the atmosphere is completely, or the ocean is completely homogeneous and unchanging. And that's needed to solve the equations on the computer, but it's an approximation which is kind of unsatisfactory. So I have a chapter in the book about this. I'm going to skip over this a little bit quickly, but I have a chapter in the book about the role of noise and how even though equations like Navier-Stokes equations are completely deterministic, there's no randomness, if you like, in that equation. Every term is well defined. When you solve these equations on a computer, it's actually beneficial to add noise to the equations to represent kind of variability within these grid boxes. And I got quite interested over the years. This is where I'm leading to, and I'm going to skip over it because of time. But I've got interested over the years in talking to computer manufacturers about actually making computers noisy. And for many applications, it would be the last thing you'd want. You want a computer to give you an exact number. You know, if you're sending money to somebody's bank account, you don't want to just add noise to the last couple of digits of the bank account numbers. But for many of these fluid mechanical calculations, actually, noise, as I say, noise is an advantage. And the thing is, you can actually introduce noise into a computer, if you like, for negative energy, because you just turn down the voltage across the transistors. They start to become noisy. So it's a very energy efficient way of introducing noise. And in trying to come up with, does nature make use of this in other aspects, it's got me very interested in the brain. And I think there's overwhelming evidence that the brain is a noisy computer, if you like. It runs on 20 watts, 6 orders of magnitude less than a modern supercomputer, yet doing much the same amount of data processing that a big computer does. But unlike computers, we seem to be creative people, and we have clever ideas. And where does that come from? And I think it comes actually from the noise in the computer. It's what gives us our crazy ideas, that we either bat down and say, that's rubbish, that's rubbish, that's rubbish. But occasionally, oh yeah, that's a good idea. So I have a chapter in the book about how in non-linear systems, noise can be your friend. It's not the nuisance that you typically think it can be. I'm going to finish with a somewhat controversial area, although it brings in another great Irish physicist, John Bell, who was from Belfast. And this is the last bit of my diagram trying to link Lorenz's geometry to some of the great physicists of the 20th century. So Albert Einstein, Niels Bohr, these are the two founders of quantum mechanics. And John Bell, who in the 1960s came up with a potential, well, it's turned out actual way of trying to distinguish the different perspectives that Einstein and Bohr had about quantum mechanics. So you may be aware there's these famous debates in the 1920s at what are called the Solvay conferences in Belgium between Einstein and Bohr about the nature of reality at the quantum level. And Bell proposed this way of testing their ideas. And sadly, Bell died in the 1990s, I think, kind of prematurely. If he had lived, he would unquestionably have won last year's Nobel Physics Prize. But it went to three experimental physicists who basically proved something called the violation of Bell's inequality. I'll try and say a little bit about it if I have time. But the media sort of advertised this result as showing that Einstein was wrong and Bohr was right. So Einstein, you may know the famous two things he said. He said, God does not play dice. So he was a great believer that the world really was deterministic. There was no randomness in the world at a deep enough level. And he also didn't believe in something he called spooky action at a distance. And spooky action at a distance is the idea that, you know, what you do over here cannot possibly affect what happens, I don't know, let's say a few million light years away, instantaneously. And these experiments cast doubt on those two ideas, at least in conjunction. So Scientific American, the universe is not locally real, you know. Now, I'm a passionate believer that Einstein was right, and I hope in the course of time he will be proven so. What I want to do, and again, conscious of time, perhaps just remind me, 5 minutes or? Absolutely, okay, because I don't want to overrun too much. The experiment was about things called entangled particles. The notion of entanglement was something that Schrödinger came up with. And Bell's experiment involves measuring, so you can have photons, particles of light, which are polarized light. And you can think of the polarization as like the little photon having a spin, having a sort of internal spin. And in the experiment, there are two experimenters which are typically called Alice and Bob, and they are far apart. This source spits out these two entangled particles which travel, you know, in opposite directions. And Alice and Bob measure the spin of these particles. But when they measure them, they have an apparatus which they align. The polarization apparatus is aligned in a certain direction. And the result of the measurement is that the photon is either deemed to be up or down, have a polarization that's up or down relative to that direction. And in the experiment, Alice and Bob have two possible directions they can set their polarization equipment. And just for the sake of argument, they do 4 sort of sets of experiments, for the sake of argument, on different days of the week, Monday, Tuesday, Wednesday, Thursday, with the 4 different settings. And then they look at the correlation of the up. If Bob got up, did Alice get up? If Bob got down, did Alice get up or down? And they look at the correlations. And this Bell thing called Bell inequality says that experimentally, this set of correlation values, don't worry about the details, can exceed a number. And the problem is that people thought that it was impossible for an Einstein type of theory, which didn't have spooky action at a distance and everything was deterministic, to satisfy that inequality. So that's why Einstein was claimed to be wrong. Now, there is an assumption here to do with what's called counterfactual definiteness, which I think I'm going to not go into at all, except to say that in physics, counterfactual reasoning is very, very commonplace. So if I was to, if the boy threw the ball to the father and the father caught the ball, and you said, well, what if the boy had thrown the ball with half the speed? Would it have reached the father? Well, you can plug the numbers into a simple formula using Newton's laws, and it'll tell you how far the ball would have gone, and you can answer that question. So Newton's laws allow for counterfactual reasoning. But when you get to chaotic systems, it's really not that simple because you have these gaps in the attractor. So if you take the view, I'm going to skip over this a little bit, but if you take the view that the whole universe is a chaotic system evolving on one of these Lorenz type attractors, where the real states of the world lie on the attractor, so they're on one of these trajectories, Monday, Tuesday, Wednesday, Thursday. And then you consider these counterfactuals, which are crucial in that Bell theorem. If you had done, let's say, Wednesday's experiment with a different setting for your apparatuses, would that have satisfied the laws of physics? And the way I've drawn this is that there is the potential for Wednesday's result to lie in a gap. Now, this provides, in my view, a completely new way of interpreting this Bell result, which could ultimately lend support to Einstein's view. What I'm going to do is finish with this slide. This is my last slide, but this is what I feel to be the message behind all this. So if you don't worry about the detail, but it's kind of relevant because earlier this week there was a big announcement from CERN that they want to build an even bigger Large Hadron Collider under the Lake Geneva and so on, sort of many, many, many tens of billions of dollars. And this is very much predicated on the philosophy that to understand more and more about the world, we need to probe smaller and smaller scales. And this has served us pretty well, I would say, in science over the years. But I question, actually, whether this philosophy might be breaking down. Because if this result about the Lorenz attractor is correct, then it's telling us that the laws of physics, at their most fundamental, may be as much about the very large scale structure of the universe as about the structure on these very, very smallest scales. And by ignoring the potential role of the universe on the largest scale, we might actually be misleading ourselves that we can formulate better theories of physics by just probing smaller and smaller scales. And to me, it's a little bit like, trying to understand Escher's famous hands drawing hands picture. By just zooming in to a tiny part of the picture, we might get some information about how clever Escher was as a drawer and a lithographer, but we get no idea about the meaning, if you like, or the sense of the purpose of the picture. So I kind of feel this really opens up quite a big kind of vista in terms of what direction fundamental physics should be going. And this is sort of one of the reasons why I want to suggest to you that chaos theory should be that third vertex in the triangle, because not only has it practical value for things like humanitarian aid in the presence of extreme weather, it also provides some insights into completely different directions which physics could go to understand better the universe and why we're here, and the very deepest nature of quantum mechanics. So with that, I will stop. Thank you very much indeed.
So, President, members of the Academy, friends and guests, it is my duty as respondent to thank the speaker for his discourse. Anyone who's ever had to give an academy discourse will realize, I think, that it is in some ways an impossible task. On the one hand, you are meant to discuss something which is intellectually stimulating and challenging, lies at the forefront of our current understanding, and yet at the same time, it should be generally accessible to a broad audience. And of course, these are contradictory aims. There's a tension here. But these are tensions which also are experienced by anyone who has to write a popular science book. And in many ways, the best discourses are those which are based on a popular book, and Tim's is no exception. And if you want to understand a bit more about what he was talking about, then I can do no better than to recommend that you buy his book. I'll take my 10% afterwards. Yeah. But more seriously, if giving a discourse is impossible, then responding to one is even harder. I mean, one would like to make some comments which put this into a context. And I think perhaps the important thing here is the real contribution to humanity that Tim has made is to emphasize the importance of ensemble modeling. And I absolutely agree. This is a key step forward. You might ask, why did we not do it earlier? And one answer is a simple and trivial one, that it demands lots of parallel computing power. So technologically, it's only recently become possible. But I think there's a deeper psychological issue which goes to the heart of what the subtext of what the various topics that Tim was addressing, which is how do we predict the future? And linguistically, it's quite interesting that we say the future. Maybe there isn't one future. Maybe we should be saying the futures. And in a way, this is the idea behind ensemble modeling, that you predict a range of possible futures. And then you can say that with a certain probability this is going to happen, but it's not definite. And this comes again to a psychological issue for humans. We hate uncertainty. We are not happy with doubt and uncertainty. We want to know what the future is going to be, and we demand precise answers, which is, I think, why we have all the quack astrologers and fortune tellers who make a lot of money pretending that they can give us a definite answer. But reality isn't like that. The reality is grey, murky, uncertain, and we have to live with it and understand it. And I would agree with Tim that I think chaos theory and the discovery of strange attractors and the very complicated dynamics that these otherwise quite simple systems can exhibit is a real step forward in our understanding. Now, I would not personally put it up on the same level as general relativity and quantum mechanics, and I think most of my physics colleagues would probably agree, but in the sense of a stimulating idea, a provocative idea, then the idea that somehow a superdeterministic model of quantum mechanics based on fractal geometry might actually resolve some of the deep, deep philosophical issues we have about, is nature deterministic or not? Is it probabilistic? These are very old issues, actually. In fact, if you go way, way back, Epicurus took over the Democritus's atomic theory, but introduced the swerve, a sort of little noise term to create a bit of chaos and randomness. So there are these ideas go way, way back. Interestingly, Newton did not actually believe that the solar system was completely stable. He felt that God would occasionally have to intervene and adjust his clockwork a little bit, whereas Laplace famously thought it would be completely deterministic and stable, which was wrong. So there are really deep issues here. They touch on issues of free will, of causality, how you understand quantum mechanics, how you understand physics. I won't delay you any longer. I just wanted to put a little bit of context around what Tim has been talking about, and once again, thank him for his discourse.
So please join with me in thanking Professor Palmer for a superb discourse. Thank also to Professor Drury for, as I said earlier, an insightful response on behalf of the Academy. I'd like to thank the audience, not just for attending, but for your participation as well. I think that's one of the really good things and different things about the discourse is that it lasts a certain length of time, the actual discourse, but the questions and answers actually really, you can learn so much more than you perhaps learn from the lecture itself. That's not to suggest we didn't learn much from the lecture, but I contrast that with a lecture within a symposium where there's a rigid timetable and the chairperson is looking at the time going, well, we've time just for one question, which seems always such a waste. So that's one of the nice things about the Academy. I know the longer we go on, we're between you and a glass of wine. I understand that, and the rest of your evening. But it really has been a really thought-provoking discourse and discussion, and I thank you for that. I'd also like to thank the Secretary of the Academy, Ms. Mary O'Dowd, for organising the Academy's discourse, and again wish her a speedy recovery. The next Academy discourse, Explaining Unionism, is now due to take place in April. The exact date is not yet available, so watch out on our website, www.ria.ie. As soon as they are available, you'll be able to find out the dates for that. Thank you all for attending this evening's discourse, and do please join us now for refreshments in the front room. Slán live go fóill. Gorv míle maith agad.